So this is the first in a series of videos where we will discuss the material that we're going to be covering this semester. We will, like I said, we will talk about sets, we will talk about indices, and we'll talk about logarithms. So these are topics that you have seen in secondary school. And the reason we're going over them now and again is to remind you of some of the concepts and then look at some applications. And because these things will play a role as you go all the way through your course. So we'll start by talking about sets, and then we will then talk about indices, and then we'll talk about logs. So these are the topics that we will cover under this lecture. So set theory is a huge topic, but we will not go through the formal set theory. One of the axioms of set theory is what are called the Zermelo-Fraenkel axioms, and they're quite long and they're quite detailed. We will not go through those, but we'll use a few informal definitions to tell us what is a set and what is not a set. So we'll start with some basic definitions of sets. A set is a well-defined collection of objects. What does that mean? It means that if you have some set, which I can denote with a square, you know when an object is in the set or an object is not in the set. So if we call this set, let's say A, and we call this element, say, small a, and then this one is called B, you can tell that the A, small a, is a member or an element of the set A. And you can tell that small b is not a member of the set B. So the well-defined there means that once you describe the set, you can tell what the members of the set are and what are not members of that set. So that's key. The term well-defined means that given a new object, you can determine whether it belongs to the set or not. Now, there are other theories of fuzzy sets where some of these concepts are relaxed, but in this case, we are going to define our set such that objects either belong to the set or don't belong to the set. There is no middle ground. So we usually would denote sets by uppercase letters. And then usually for large sets like the universal sets, we may use U or E. And then we'll also have special symbols for subsets of real numbers. Okay, so if, like I said here, this A, the small letter A is a member of the set A, we'll write A belongs to A. And in this case, we would write B does not belong. So we cross out the belongs to say that the element B does not belong to the set A. So if A is not a member, this is how I would write it. So once you describe your sets, you know what are members of that set and what are not members of that set. So these are some examples. We have three sets. The set A has the numbers 1, 2, all the way to 24. So it's got 3, 4, 6, 8, 12, and 24. It doesn't take long to see that these are factors of 24. So that set A is describing the factors of 24. But it doesn't take long to say that, well, we can rewrite them in other ways. Consider the set B. The set B is described as the set of elements X, such that X is a factor of 24. In other words, these are the set of factors of 24. Or we can just write C. We have our brace for our set notation, and then you have factors of 24. And so A, B, and C are describing the same set. You see that A equals B equals C. These sets are the same. In the set, in the case of A is written by listing or enumerating the members of the set. B and C are written using what is usually called set builder notation. So you give us the property that they all satisfy. In this case, they are all factors of 24. So we're describing the set B and the set C as a set of factors of 24. In the case of A, we're going ahead to list the factors of 24, and all these sets are the same. And so set notation may vary. There are different ways in which you write them. Later on, when we are dealing with subsets of the set of real numbers, we may also then add what we call interval notation. So we'll write them as the numbers between two numbers, one on the left, one on the right. Okay, so let's discuss some properties, elementary properties of sets. The first one, if A and B are sets, and every element of A also belongs to B, then we say that A is a subset of B. So you can draw it this way, where this B is a set B, and then the set A is contained in the set B. So every member of the set A is a member of the set B. So we say that A is a subset of B, and this here is a subset notation, right? If and only if, when A belongs to A must belong to B. So in other words, every member of A is also a member of B. We say that A is a proper subset of B if there are elements in B which are not in A. So we sometimes will use this notation. So we say A is properly contained in B, or some books will just use this. Now, if A is a subset of B and B is a subset of A, it means that all the members of A are members of B, and all members of B are members of A. So then A must equal B, and vice versa. So if you go back to our example of the factors of 24, you'll notice that any number that is a factor of 24 is in A, and any number in A is a factor of 24. So these sets are the same. These are important because later on, you have to show that two sets are equal. If the sets are not small, but what I mean by that is that they have quite a lot of elements, you may have to use these set properties to show that the sets are equal, or subsets, or proper subsets. So all those are important.